Welcome guys to this video. Here we'll be learning how to prove some trigonometry identities using the right angle triangle. Now we have this very common identity that cos²θ plus sin²θ is equal to 1. The question now is prove that this is true. Prove that cos²θ plus sin²θ is equal to 1. Now let's start. Let's make a right angle triangle. Okay. Here we have this to be the angle, mark theta, the opposite to the angle, the adjacent, and we have this to be our hypotenuse. Alright. Now what is sine? Sin theta will be opposite of our hypotenuse. Therefore, sin²θ will be what? Opposite square over hypotenuse square. That is our sin theta. Our sin²θ. That's our sin²θ. How about our cosine²θ? It should be adjacent square over hypotenuse square. That's our cosine²θ. Now, the sum of these two tricks will resolve to 1. That's what we are asked to prove. Therefore, sin²θ plus cosine²θ should be this. So that means opposite square over hypotenuse square plus adjacent square over the hypotenuse square will be equal to what? Let's prove. Let's try to solve it till we get 1. Now, you know here we have the two denominators are the same. Therefore, we take one of the denominators and we add the numerators. So taking the LCM, okay, there we have O square plus A square. Alright, O square plus A square. Now from your Pythagoras rule, can you remember your Pythagoras rule? Which states one side is equal to the squares of the other two sides. So from our Pythagoras rule, we will have that the square of this side, that the square of the hypotenuse side is equal to the sum of squares of the other two sides. That is, h square is the same thing as saying O square, that is opposite, plus the adjacent square. That is according to our Pythagoras rule. Now looking at this, you would see that O square plus A square here resolve to give you what? H square. Therefore, A square to be H square. Is that okay? We'll have it to be H square over H square. And H square over H square resolves to 1. Therefore, we have proven that cos²θ plus sin²θ is equal to 1 using a right angle triangle. Here's another example. Now let's prove this, that cot²θ plus 1 equals to cosec²θ using the right angle triangle. You have the theta angle, opposite to theta, adjacent to theta, and hypotenuse. Now, here is the question. How are we going to prove this? We're going to prove this by solving for the both sides. Now, the point, the exact point in which the both sides are the same, then we have proven the equality sign there. Let's prove. Let's start. Cot²θ is what here? Cot²θ is noted to be the inverse of tan²θ. Now, what is tan²θ? Tan²θ is simply opposite square over adjacent square. Because tan theta is opposite over adjacent, then tan²θ is opposite square over adjacent square. Now, the inverse of this will be adjacent square over opposite square. Simple as that. The multiplicative inverse of opposite over adjacent is adjacent over opposite. So cotangent ²θ is adjacent square over opposite square plus 1. What is the right hand side? The right hand side is cosecant ²θ. The right hand side is cosecant ²θ. Here is another explanation. Cosecant ²θ is inverse of sin²θ. Inverse of sin²θ. And sin²θ is what? Opposite over hypotenuse. Sin²θ is opposite square over hypotenuse square, because sin θ is opposite over hypotenuse. Therefore, sin²θ will be opposite square over hypotenuse square. Opposite square over the hypotenuse square. Here we go. Let's solve the both sides. Now, here we will have the LCM here. The LCM will be a square plus, the LCM is what? Opposite square, alright? So we use it, we solve, and we get here that a square plus opposite square, that's what we get, is equals to, now on this right hand side we have that the inverse 1 over opposite square over hypotenuse square will simply mean hypotenuse square over the opposite square. Now this begins to make sense. We can see that the denominators are the same. Are the numerators the same? The answer is yes. Now look at these numerators. In the last example, we said something about Pythagoras rule. Just looking at this, then you would know that a square plus o square is h square. From the Pythagoras rule, that the square of the hypotenuse side is equal to the sum of the squares of the other two sides. Therefore, that means that a square plus, this one and this one are the same. That means that a square plus o square is equals to what? H square. Therefore, this is true. Therefore, this identity is true. You can say therefore the left hand side is equal to the right hand side. That proves the identity. Here we have 1 plus tan² equals to sec²θ. That's the question. And we should prove this. Proving this will make the left hand side the same thing as the right hand side. So how do we start? What is tan²θ? Tan²θ is simply, we have 1 plus, tan²θ is simply opposite square over adjacent square. Now, the right hand side is sec²θ. What is sec? Sec is the inverse of cosine²θ. So, sec²θ would be inverse of cosine²θ. Cosine²θ. Now, what is cosine²θ? Cosine²θ is adjacent square over hypotenuse square. Therefore, inverse of cosine²θ is hypotenuse square over adjacent square. Alright, now the left hand side we solve. You know, these are two fractions. Let's get the fraction with a common divisor, which is the LCM there. Okay, we now multiply through, we have this. Alright, here we have this, that this is equals to this. Still the same thing, almost the same thing as the last example. We can see clearly that the denominators are the same. You know, we want to prove where the left hand side and the right hand side are the same, then we know that we are correct, that this identity is true. So here we have that the denominators are the same, so the numerators ought to be the same as well. And you know, I believe you know that the numerators here are the same from your so-called Pythagoras rule. A square, adjacent square plus opposite square is always given to be the other side, the square of the other side, hypotenuse square is equals to the hypotenuse square. Therefore, this identity is true.